In this next section, we want to look at doing integrals of what are called rational functions, that is to say, ratios of polynomial functions. We're going to assume that the degree on top is less than the degree on the bottom. If it's not so, then as we'll see, we can do long division to make it this way. Before we get officially started on this, I want to reverse engineer some ideas here. I want to think about some fractions. Supplying the missing factors and simplifying, I see that I end up with 6x minus 13 over x minus 2 times x minus 3. As another example of this, think about 2 over x plus 1 plus 4 over x plus 3 plus 5 over x. This time the common denominator is going to be x plus 1 times x plus 3 times x, and we can write this as a single fraction as before. After doing all the required algebra, I find out that the fraction that I finally get is 7x squared plus 27x plus 15 over x plus 1 times x plus 3 times x, which I can then disguise by multiplying out the x plus 1 times x plus 3, and then by multiplying by x, increase the power on each term. This suggests the following strategy. If I have a rational function p of x over q of x, where p and q are polynomials, the degree on top is smaller than the degree on the bottom, and the bottom can be displayed as a product of distinct linear factors, then it might be possible to write p of x over q of x as a constant divided by the first distinct linear factor of the bottom, plus a constant divided by the second one, and so on and so forth. This forms the basis of what's called the method of partial fractions. For example, if you look at the fraction x plus 1 over x squared plus 5x plus 6, which obviously can be written as x plus 1 divided by x plus 2 times x plus 3, it's possible that we can write that as a constant divided by x plus 2 plus another constant divided by x plus 3. It's worth mentioning that this formula doesn't even make any sense at x equals negative 2 or negative 3 because I get division by 0. If I wanted to be picky, I would say I want this equation to be true for all x values except x equals negative 2 and negative 3, where it doesn't make any sense. Assuming for the moment that we're not looking at one of these bad spots, multiply through by both x plus 2 and x plus 3. X plus 1 should always equal a times x plus 3 plus b times x plus 2, except when x is negative 2 or negative 3, which I should never put into this formula. Consequently, I'm going to put those numbers that I should never put into that formula into that formula. I'm not actually going to do that, except that I do. Really, what we're doing is, this quantity is a polynomial involving x, and so is this. Polynomials are continuous functions. When you take the limit of a polynomial, it's the same as plugging the number in to the polynomial. When I take the limit as x approaches but is never equal to negative 2, that's the same thing as just sticking x equals negative 2 into this formula, and likewise for x equals negative 3. It's going to look like I'm doing what I said I should not do, but if you think about the limit business, then everything is all right. So really I'm taking the limit as x tends to negative 2. Doing so, I find out that negative 1 is a times 1 plus b times 0. That tells me that a has to be negative 1. If I do the same with x equals negative 3, it develops that negative 2 needs to equal negative 2 times b, which tells me that the b should equal 1. The usefulness of this is that if I have a rational function and I can split it up in this way, as we've just done, then it makes it easy to integrate. This technique is called the method of partial fractions, and in the case where the denominator has distinct linear factors, it is particularly easy to deal with. As another example, look at the integral of 1 over x cubed minus 4x. The denominator is going to factor into nice distinct linear factors here. I can factor an x out, leaving x squared minus 4 behind. X squared minus 4 is x plus 2 times x minus 2. So the denominator factors into x times x minus 2 times x plus 2. And hopefully we'll be able to find constants a, b, and c so that the fraction that we're interested in is actually equal to a divided by x plus b divided by x minus 2 plus c divided by x plus 2. I'm going to multiply through by the denominator on the left to clear the fractions. If x is 0, then this term is 0, and that term is 0. 0 minus 2 is negative 2. 0 plus 2 is 2. This tells me that 1 and negative 4 times a must be the same number. This tells me that a must be negative 1/4. If x is equal to 2, then this term is 0, that term is 0, the middle term is b times 2 times 2 plus 2. 4 times 2 is 8. This tells me that the b must be 1/8, and if x is negative 2, this term is 0, that term is 0. 1 must equal c times negative 2 times negative 2 minus 2 is negative 4. 1 is equal to c times 8. c must be 1/8 as well. Since I have 3 distinct linear factors, the a, the b, and the c are easy to determine. My partial fraction expansion tells me that if I can integrate negative 1/4 divided by x and 1/8 over x minus 2 and 1/8 over x plus 2, I'll have my answers. Negative 1/4 and 1/8 are constants, though, so I can carve this up into 3 integrals and write my answer in the following way. Depending on my purposes, I might just leave it in this form, or I could use algebra and properties of logarithms to simplify things if I wanted to. This time, I'll use properties of logarithms to simplify things. Using the properties of logarithms that we know from algebra, I can combine all of this stuff into a single logarithm if that was more useful for my purposes. If the bottom of the fraction has repeated linear factors, that's going to cause a small complication, which we will look at in the next video. And also, it's possible that you could have a quadratic as a factor on the bottom of the fraction, yet not be able to decompose that into the product of two linear things. We'll call those irreducible quadratic factors, and we'll deal with them in an upcoming video as well. I hope that everybody's having a good day. I'll talk to you again soon.